So today I'm going to give my last lecture on modeling the spread of infectious diseases. So I had to think about, what do I do tomorrow? So tomorrow I'm going to do something which is recent work, which is not in the book, but I think it's my most interesting project, and that is modeling the fish biomass in a natural coral reef, and using that to understand the impact of fishing. And if you don't want to come in one sentence, we're going to actually be able to prove fishing is very bad. Any type of fishing is very bad. So that's what I'm going to do tomorrow. So somehow what I'm doing this up until today is kind of trivial. So tomorrow I want to do kind of a case study, sort of talk about one project for the 50 minutes. And I'll show you what I think is just a great picture at the end to sort of motivate you to come tomorrow morning. So we've been talking about, just a quick review, modeling the transmission of infectious diseases. Last lecture, we extended the basic SIR model to include demography or vital rates, right? And then we were in the process of extending that to allow the transmission parameter, transmission coefficient, to be time dependent. So I'm going to continue talking about that today, and then I'm going to discuss some recent work modeling, again, indirectly transmitted infectious diseases like cholera. So this is the schematic for the SIR model with vital rates. So we have an influx of susceptibles, births, natural births at a rate n times mu, and then we have natural deaths of the same death rate. And we proved the theorem essentially that R0 is the critical threshold, that if R0 is less than 1, the disease dies out. If R0 bigger than 1, then we have endemic disease, right? So this is, of course, different than without the vital rates. So as long as you start with a positive number of infectives at time 0, over time the number of effectives is approaching this number. So you always have disease in the population. So the endemic disease state, that equilibrium point, is globally attracting, at least for the interior of the first quadrant. And as we discussed, that equilibrium point could be an attracting node or it could be a spiral. So in the case where it's a spiral, solutions oscillate. So what this is a figure of is actually quite interesting. So this is a simulation of the SIR model with vital rates with realistic parameters for measles from the United Kingdom in the 50s. And you see, first of all, the oscillation. This is the oscillation of the number of susceptibles. That's the oscillation for the number of infectives. And you see a 2-year period. Now, of course, you see the oscillations decaying somewhat quickly to 0. Somebody mentioned last class that, this is the real data set. So you see the 2-year oscillations in the data set. But of course, the oscillations are not decaying to 0. Now, somebody said, well, the eigenvalues for the Jacobian matrix here were pure imaginary, then the oscillations would not decay, right? On the other hand, that doesn't happen with realistic parameters. You might wish it happens. I know many people that wish it happens. But you can't choose your parameters. You can't choose how long somebody is infected for. So with the realistic parameters, you get the oscillation with the correct period, but you don't get the sustained oscillation. So something is missing from the model. Okay, so then I mentioned 2 extensions. One extension is adding an exposed class to account for individuals that are infected but not yet infectious, and then also allowing the transmission rate to be time dependent. And again, you think that usually you get a cold or flu virus more in the winter than you do in the summer. Okay, so for the first extension, we discussed the SEIR model with vital rates, and this is the exposed class, so the susceptibles enter the exposed class at rate beta, the exposed individuals enter the infected class at rate alpha, and so on. You have the same death rate in each class, and then you have the births at rate n times mu, and then we saw that, sorry, again, the total population is conserved. With this new R naught, we prove a theorem which is very much like theorems 1, 2, and 3, right? So if R naught is less than 1, the disease dies out. If R naught is bigger than 1, then you have endemic disease. And in fact, you have, over the long term, the same number or same proportion of infectives as you did without the E class. But then I mentioned, it's not worth spending much time trying to show you this, but if you're interested in predictive models, then the E is sometimes important because that slows down the growth of the infectives. And there's examples where this does a much better job of modeling real data than without the E. Okay, and I also said that this, if you open a journal on infectious disease modeling and it uses an ODE model, then it usually kind of starts with this type of model. Okay, now we add a time-dependent transmission rate to the SEIR model. So again, there's lots of data to show that for childhood viral diseases, mumps, rubella, chickenpox, and again, think pre-vaccination, but also for cold virus or flu virus or non-exotic flu virus, the contact rate beta changes throughout the school year. I mean, this is very well documented. So obviously it's higher when school is in session, and it's lower during the summer months, it's lower during Christmas vacation, lower during Easter vacation. So what authors have been doing for the last, and I forget now, maybe not much more than 5 years. Maybe that's not true, maybe 10 years. But certainly there are a number of recent papers on this, is they've been letting beta of t be time dependent. At first, authors have let beta of t be a sine function. And again, it's higher during the winter, smaller during the summer. And then after that, people started using a Haar function. So it's high during the first semester, then low during the Christmas break, and then high during the second semester, then low during the summer, and then it repeats. So the important thing is both of these are 1 year periodic, obviously. Okay, so let's start by talking about what people have done, and I'd say there's a dozen papers on this where beta of t has this form. Okay, so here is a bifurcation diagram where the bifurcation parameter is alpha. So this alpha, which I think they call seasonal forcing. Now the parameters are not very realistic, right? Because here you're just varying one parameter. And, well, let me take that back. The parameters are realistic except for alpha. Okay, they're letting that change. And this is what you get. So it looks like there's very complicated dynamics, right? There are period doubling cascades, there's chaotic behavior, there's interior crises, boundary crises, and so on. this type of thing I consider kind of a gift from disease modelers to dynamicists. Because no one who working in dynamical systems would think of a model like this. Right? None of us, I mean, at least me, probably in 1,000 years, I would never write down a model like this if I wasn't thinking about epidemics. So this is an example. This is a model that obviously has some very complicated dynamics. It may have some new dynamics. It may have a new or several new global bifurcations. It may not. But the point is that it's a new example for dynamicists to study coming from modeling infectious diseases. Now, several years ago, actually, I think my first actual paper in this business was studying a low-dimensional population model where, which wasn't biologically realistic, and we had a bifurcation diagram, which is actually more complicated than this, and we actually had one was in 2 dimensions, or for 2 generations, one was for 3 generations. We had an attracting, this is for a mapping, not an ODE. We had an attracting invariant closed curve, which if you vary the bifurcation parameter a little bit, bifurcates into a strange attractor. And by studying this family of models, we found 2 such examples, and we were able to understand the bifurcation cascade, and they were new. There are only about 6 or 7 other examples known of attracting closed curves bifurcating into strange attractors, and this gave 2 new phenomena. And what's more is that there's a conjecture of York, Grabogi, and Ott on essentially how this can happen. And their conjecture is for invertible maps. Our map is not, or our mappings are not invertible, but the non-invertibility seemed benign. I mean, we understood sort of the non-invertibility locus, and it seemed to be far away from the interesting dynamics. But the point is, so it seemed like one of our examples was violating the conjecture. So the conjecture, I don't want to state it precisely, but there were always homoclinic tangencies present when you had such a bifurcation cascade. And we got, especially my graduate student, got to be very good at finding homoclinic tangencies and couldn't find one in one of these examples. So this could be, then he graduated and started working on other things, but this could be a counterexample to a pretty big conjecture. And again, I would never in a million years have thought up that example as a counterexample, but it just arose from studying a population model and me sort of keeping my eyes open as a mathematician looking for interesting dynamics. Okay, sorry for the diversion. Okay, so what's known about this model? Now, of course, it shouldn't be very surprising that you have such complicated dynamics, because we're essentially starting with a nonlinear oscillator, right, that exhibits periodic behavior, and then we're forcing it. We're periodically forcing it. So probably most people here know examples of just a simple pendulum, which if nonlinear pendulum, which if periodically forced exhibits all types of chaotic behavior. So in some sense, this shouldn't be so surprising. Okay, so as far as I know, there are no rigorous results. I know only one mathematician who kind of looked at this, but not very seriously. And he proved what too many mathematicians prove, and that is, well, I can't prove anything about this, so let me change this, and let me change this, and make it totally non-biological, and then I can prove something. Okay, so numerically, you can see attracting periodic orbits of period 1, 2, 3, multiple coexisting periodic orbits, chaotic dynamics, as I said. But the question is, does this model explain the measles data? Okay, so the model exhibits undamped oscillations of all the frequencies that are observed in the measles data. And I'm just showing you essentially one aggregate data set where you see the 2-year cycle, but I can show you data sets for some special cities where there's a 1-year cycle, and I can show you some data sets where there's some funny switching. So the model produces chaos, which can explain some irregular behavior and transitions from one type of period to another, and I don't want to talk about that. But with realistic parameter values for everything, the model predicts that the number of infectives goes to 0. So it doesn't explain the data. Okay, so now how about if instead of looking at the forcing by the sine wave, we look at the forcing, the transmission rate being the Haar function? Well, here, I'm just stating the facts, there's a single periodic orbit of period 2 years. That's good. And it's good because it agrees with the aggregate data that I showed you. It agrees with data in many cities. On the other hand, there are some cities that exhibit 1-year cycles. So this model can't explain that. As I said, there are also some cities that exhibit some transitions from one cycle to another, back to the other cycle. It can't explain that. So very recently, some authors have started adding variable birth rate. So they studied the birth rate over this period in the 1950s, and they saw that it wasn't really constant. So they tried to adjust for that. Okay, now I don't want to follow that. Frankly, I'm not so interested in that, because I think both of these are kind of wrong. So that's what I want to talk about. So this is very recent work. Hao Wang was my postdoc until a month ago. He's now at the University of Alberta. Mark Polycott is my longtime co-author. And the question is this. In the simplest SIR model, will we allow beta to be time dependent? Okay? Suppose I tell you I of t. Okay, so we have this model. We have the two parameters, we have beta of t and we have nu in the basic model. Everyone remember the basic model? Monday was a long time ago. That's the basic model. So I should tell you, I would feel very uncomfortable talking in a mathematical seminar about this because the mathematics is so trivial. Most of you are students, so I don't worry about that here. But I'm absolutely serious. The mathematics here, as you're going to see, is trivial. On the other hand, I'm willing to bet that this paper is cited 20 times more than any other paper that I ever wrote. So you don't always need very sophisticated mathematics to make significant contributions in biology. You should remember that. I mean, sometimes you do. As I'm saying, sometimes the biology is driving mathematics. That's why I started in this business. But sometimes simple mathematics will solve a problem. Okay, so the question is, I'm given I of t. Can I find beta of t such that the solution of this differential equation, let me say it this way. I'm given, I didn't have to write it. Sorry. I'm given f of t, a positive function, on an interval from 0 to big T. So this is a mathematical question. You're never given continuous data for an infectious disease. That's kind of silly. But let's solve the mathematical problem, and then I'm going to approximate to solve the real problem. So I'm given a positive function on this compact interval. Okay? And then the question is, can I find, say, nu, and the function beta of t, such that the output of this model, I of t, is equal to f of t for all time in that interval? That make sense? So it's an inverse problem. And again, I've never thought about it. I've been thinking about differential equations for a long time now. I've never thought about asking a question like that. But it's totally natural, I think, thinking about, recovering the transmission rate from number of infections. So again, biological problems can generate new mathematics, but it can also generate new questions about old mathematics. Okay, enough propaganda. That's the question. And at first, I thought it was impossible to answer, and I put it down, and then I looked at it again, and then started proving little things, and then Mark Polycott came to visit, and we proved little things. But the answer is yes. And there's an explicit formula, and the answer involves a first-order differential equation where you can just solve it. And it's even worse than that, because this is the type of mathematics which I'm trying to eliminate from the differential equation curriculum at Georgia Tech, because I say it's totally useless. You don't teach anymore how to exactly solve differential equations. You teach them sort of qualitative analysis. Don't tell my colleagues. Okay, so the idea is incredibly easy. What we're going to do is we're going to take this equation, and remember, we want I of t to be f of t. Okay, so we're going to take the second equation and we're going to solve it for s. That's what that is. I should tell you, this has been open for about 70 years, this question. And there are books, including sort of the Bible of infectious disease modeling, which says you cannot recover beta of t from I of t. So this is step one. You solve for s of t. And step two is you take this s of t and you plug it into the first equation. So when you do that, we're going to get a differential equation for beta of t. So what differential equation do you get? Well, you just have to do a little bit of calculus, and this is the differential equation you get. Beta prime of t minus p of t times beta of t. Now p of t minus f of t times beta squared of t is equal to 0. F you're given, and p of t is this function cooked up from f prime, and f prime prime, the first two derivatives. So this, of course, is a first-order nonlinear differential equation. The nonlinearity is quadratic. Bernoulli told us to change coordinates, let x be 1 over beta, and if you do that, this nonlinear differential equation gets transformed into a linear differential equation. So then you use the method of, I think, integrating factors, that's what I would call it, to just write down the solution. So 1 over beta of t is equal to x0 e to the minus L. This is big P of t, which is the integral from 0 to t of little p. And that's it. Doesn't get easier than this. Now, there's ambiguity here, because you see that this inverse problem is very underdetermined, in the sense that x0, which is 1 over beta of 0, is arbitrary. And this function, big P of t, well, the function little p of t, it's not, that doesn't have to be monotone or anything like that. So this is kind of a complicated function, so e to the minus big P of t is kind of a complicated function. So the ambiguity isn't a constant, it's much more complicated than that. But here are infinitely many solutions. Okay? Okay, now, let's go back, sorry. Is this well defined? Well, this is all well defined provided that P of t is well defined. And as P of t is well defined, as long as that denominator is not equal to 0. Now, I told you that f is positive. On the other hand, this expression could be 0. Now, if you allow me to choose nu, which biologically is totally stupid, but we'll come back to that. If you allow me to choose nu, then of course I can choose nu large enough such that that denominator is never 0. So if you allow me to choose nu, then I can always recover beta of t, provided I choose nu sufficiently large. On the other hand, what is nu? I mean, of course I can't. I mean, now let's think biologically. 1 over nu is the period or duration of infectiousness, right? That's fixed by the disease. We don't get to choose that. God gets to choose that. So what if you're given nu? Well, obviously, you want this thing to be... You can't do the inversion if this is 0. So we need to require that this expression, f prime plus nu times f, is positive, is non-zero. Okay? And actually, to be honest, the measles data that I showed you, I think was from 1958 to 1968. It actually went to 1970. But those last 2 years, we had problems with this. So I'm not showing you that. Now, I have ad hoc ways to deal with this, but we're still trying to understand that. I mean, you can scale f in various ways, and you don't have to be very clever, and you can deal with this denominator being non-zero, but then you need to see how that changes the solution. So that's a little bit of work in progress. Okay, so now, again, real life. Data is discrete. Okay, measles data, again, historic measles data reported every week. Swine flu data, certainly in the United States, reported every week. So how do you go from this mathematical question where you're given a continuous f of t or a smooth f of t to given data? Well, it's very simple. So you're given the discrete data, and you apply a spline, and we use like a 7th, 8th order spline, or a rational approximation to obtain a C2 function f of t. And then we apply the inversion formula. And you can prove various things that this works well. This works. On the other hand, remember we have this non-uniqueness issue, right? This extra functional term involving x0 or 1 over beta and the beta 0, which, if we can't say anything about that, in a practical sense, this isn't very useful. Okay, so let me show you that for measles in the UK, this new inversion method says something interesting. And for it to say something interesting, then the sort of ambiguity is sort of minor. So again, this is the infection data from 1948 to 1958. This is a spectrogram. So I did a fast Fourier transform of this data. So you see the biggest spike at frequency 1/2, which corresponds to twice every 2 years. And then you see the next largest frequency at once per year. Okay, so this data set, again, has the largest, most power in the 2-year cycle. Then what I did was we used our algorithm on this data set to recover beta of t. So what beta of zeros did we use? We chose the biologically reasonable range for beta of zeros. So we asked some experts, So I think we started in January, which is where the transmission, January 1st, school holiday, so where the transmission rate is low. And we asked a couple of experts, what is the reasonable range of beta zeros? And that's what you're seeing here. So you see you see inversions of the data for 3 beta of zeros corresponding to 3 different beta of zero. For 3 different beta of zeros, at the 2 extremes and I think in the center of the interval of the biologically plausible beta of zeros, these are the corresponding beta of t's. And just looking at them, they almost look like vertical translations. Right? Again, they didn't have to look like that. They could have looked totally different. But at least for measles, they look like vertical translations. So again, this is the spectrogram for the number of infected, and these are the 3 spectrograms for the 3 beta of t's corresponding to those 3 different beta of zeros. And you see for each of them, the main spike is at period twice per year. So we are pretty confident in saying that the real beta of t for measles, again, in the UK during this time interval, if you believe in the SIR model, S-E-I-R model, I didn't say that. So here I was just talking about this inversion problem for the SIR model. We actually can do this inversion procedure for any model. So we actually did it for what you're seeing here. What you're seeing here is the inversion for SEIR plus SEIR with vital rates with time-depending beta. Okay, so these are the 3, again, spectrograms for the corresponding beta of t's, and you see that the main spike has period twice per year. So this is the HAR function of the so-called state-of-the-art measles model. And this is the beta of t corresponding to the beta of naught that these researchers used to construct their HAR function. So does this look like that? Or does this look like a, sine wave? Of course not. So what we conclude is that the transmission rate, which everyone else was assuming sine wave or HAR function with period 1 year, we find that that's not right, that beta of t has a strong 2-year signature. And then the question is, what's responsible for the 2-year cycle, and so on. So this is like one application of our new method. Again, I wanted to show this to you, that you can do interesting mathematical biology sometimes using elementary mathematics. Okay. Any questions before I go on? Okay, so now I want to talk about another piece of recent work. This is less recent. This appeared a few months ago in the Bulletin of Mathematical Biology. The title of the paper was Modeling Reservoir-Mediated Infectious Diseases with Immunological Threshold. My co-authors are, again, Hao Wang. Josh Weitz is a biologist at Georgia Tech, and Richard Joe is his graduate student. So you look at the title, you see reservoir-mediated, and you see immunological threshold. So why reservoir-mediated? So some infectious diseases are not transmitted through direct person-to-person or animal-to-animal or plant-to-plant contact. So you all know cholera, schistosomiasis, malaria, although malaria isn't transmitted through a water reservoir, so I'm not really going to talk about that. Dengue, giardiasis, and so on are transmitted indirectly, right? If I have cholera and we have lunch together, he's not going to get cholera. right? The only way he's going to get cholera if he drinks water that I contaminate. Okay, schistosomiasis is transmitted by a flatworm. You don't need to drink the water, you just need to swim in the water, right? And the larvae sort of tunnels through your skin. Okay, so the transmission for these diseases occurs when a susceptible individual ingests or contacts water containing the pathogenic bacteria or the parasites. So goal number one for this project was to develop a framework for modeling the transmission of water reservoir-mediated infectious diseases. And we had cholera in mind, and we had cholera in mind because of discussions that I've had at Emory University's biology department with people like Bruce Levin, who's studying the ecology of cholera, which I'll talk a little bit about. But this work, for me, was certainly motivated by discussions with biologists. Sort of just hanging out, trying to spend my Fridays, if I could get away, at the biology department at Emory. Why immunological threshold? So if I drink 100 V. cholera bacteria, I'm not going to get sick. My native immune system will beat down the beginnings of an infection. Even 1,000 V. cholera bacteria, I'm not going to get sick. So they've done studies, presumably with graduate students, on how many bacteria one needs to ingest to get sick. I mean, to develop full-fledged cholera. And the answer varies from about 10 to the 3 to 10 to the 8th. So again, there's a threshold. If you ingest less than that, you're not going to get sick. So goal number 2 was to add this threshold to transmission models, and then try to deduce consequences for the control. Okay? There are some fascinating open questions about cholera. So, for instance, how do people get sick? How do people get cholera? So let me think not maybe Amazon, but let me think South Asia. Okay? People don't, so many diseases, most diseases, I guess, you have infected people coming into the population, and then the local population gets infected. But that doesn't happen this way for cholera, at least again in South Asia. That somehow cases just almost spontaneously appear not too long after the monsoon season, which I think is now. Okay, so it's not infected individuals coming into the population that gets other people sick. Somehow the outbreak just almost spontaneously begins. How does that happen? It's an extremely interesting question, which I'm not going to say very much about today, but I'm hoping in the next couple of years to help use mathematical modeling to answer that. Okay? And then how do they end? They seem to end after, several months. Kind of just end. What makes them end? Okay. I'll say something about how do they begin. I'll tell you the theory, which is being tested in Bruce Levin's lab, because he has, so the theory, basically, it's due to Rita Caldwell, I think like 10 years ago, and the idea is that the monsoons cause mixing of waters, salt water and fresh water and estuaries, which does things like reduces the salinity. So cholera doesn't like to live. The cholera bacteria doesn't like to live in the fresh water or the salt water. But when the waters get mixed, it has more nutrients, it has a higher temperature, it has lower salinity, and that's the water that the cholera bacteria like to live in. Okay, so after the monsoons, water gets mixed. That leads to a growth of what's called phytoplankton, algae. When you have this growth of phytoplankton, that's followed by a growth of what's called zooplankton. And it's known that the V. cholera bacteria attach themselves to what are called copepods, a type of zooplankton. So for the V. cholera to, and one more thing, the cholera bacteria are there always, but in a dormant state. They're everywhere. I mean, all the rivers in the United States, they're there, but in a dormant state. And for them to come out of their dormant state, they need, in particular, copepods to be able to attach to. So that's kind of the story, that the rains cause the mixing of the waters, cause a phytoplankton bloom, cause a zooplankton bloom. Then the V. cholera bacteria spores somehow turn on, go out of their spore state, become real bacteria again, attach to the copepods, and you have an outbreak when people start drinking the water. So my colleague at Emory has cholera in his lab. He has the copepods in his lab, and they're doing various experiments. In fact, they think it's him and one of his graduate students think it's very funny for me to give me the Petri dishes with the V. cholera in it for me to hold it. And once when I did that, I had a stomach ache at night. But it wasn't cholera, luckily. Okay, so I want to focus on how do cholera epidemics end. I need to say a little bit about phages. So I don't know if people here know about phages. So phages, or sometimes called macrophages, are viruses that infect bacteria. There are amazing statistics that every 48 hours, half the bacteria in the world get killed by phages. And the V. cholera bacteria has several so-called lytic phages, meaning phages capable of killing it. And these are actually some pictures of them. So goal number 3 is, can phages be responsible for ending the cholera outbreaks? And I'll show you, hopefully, in a little while, the motivation for this question. But this is one of the questions that arose from data. Is it possible that it's the phages which are ending the outbreak? So obviously they kill the bacteria, the V. cholera bacteria in the water supply. Okay, facts about bacteria, cholera, we don't have to talk about. Okay, so this is a schematic of the model. And I should tell you that, this is, I'm using slides which are several months old. This paper appeared, and there's some previous work, including by Bruce Levin, my colleague at Emory, and also Claudia Codesu at Fiocruz, who I'm actually going to meet on Monday. So we have the S, the I, the R class. We have natural births and we have natural deaths, although the picture would get too complicated if I included them, but they're there. We also have the bacteria reservoir. The bacteria reservoir has its own dynamics. Those that are infected shed bacteria into the reservoir, so they're adding to it. And the only way people who are susceptible become infected is through contact with the reservoir. So we want to create a model out of this, and we want to also include the fact that a person will not get, an individual will not get sick unless they ingest a certain amount of, a threshold amount of bacteria. So this is our model. So let's focus on the transmission function first. So C is the threshold, sort of the immunological threshold. How much bacteria a person has to ingest, and actually here it's better to be working with density rather than numbers. So how much bacteria does a person have to ingest to get sick? Well, if they ingest less than C, they won't get sick. Okay? And then the more they ingest, the larger this function. And this is the function. It's obviously it's not a smooth function. It's continuous, but it's not smooth. So that's going to imply that this system of differential equations is not a smooth system. So that's one complication. Okay, so now let's look at the system. Let's look at the last equation first. So you have the bacteria in this reservoir. It has its own dynamics. We assume that it has logistic dynamics, which is what I talk about at the beginning of the notes. So in particular, there's a carrying capacity K. So if there were no humans around, you just have this bacteria in the reservoir, K is sort of the natural density of the bacteria over the long term. Okay, so if you start with a bacteria density less than K, then the bacteria will grow to approach K. And if somehow you can start with bacteria which is density greater than K, then it will decrease to K. So this is sort of the internal dynamics inside the reservoir for the bacteria, assuming there's bacteria there independent of the humans. And this is the shedding. So we're assuming that each infected individual contributes bacteria into the reservoir at that rate. Okay. Here, so of course we have the natural deaths. We have infecteds becoming removed or recovered. Actually, there's an error here. Sorry. I think. No, that's right. No, I'm sorry. Never mind. So this is the important term. So how is the number of infectives changing? So of course there are deaths, there's recovery, and then there's alpha of beta times S. So the point here is if the density in the reservoir is sufficiently low, below the amount needed for transmission, then this term is 0. Okay? On the other hand, it doesn't much matter, let's exaggerate it, if there's 10 to the 100 or 10 to the 200 density of bacteria in the reservoir. It's not going to matter very much for the transmission of the disease. That's why you have this asymptotic value. Does that make some sense? Okay, that's the model. Now, there are no phages here yet, but just wait a few minutes. Okay, so this is what we can prove. We define this complicated parameter. Let me begin. I claim there's no natural notion of R naught for cholera. That's an exercise. We define this parameter zeta, which is kind of complicated. And if I work very, very hard, I can give you a biological interpretation, which frankly I don't understand very much, so I'm not going to do that. So here's the theorem. Oh, I'm sorry, one more thing. Let me go back here. This is mathematics. We actually study, so we don't know what this transmission function really is biologically. We know that it should have this form, but there are lots of functions which are 0 up into C, and then they're monotonically increasing with an asymptote. So we actually study the infinite family of transmission functions where we put an n here, an n here, and an n here, where we let n be 1, 2, 3, 4, 5, and so on. Okay, so if the threshold for infection is less than the carrying capacity for the bacteria, then the disease becomes endemic. Okay, since we don't have that much time, let me just use words rather than sort of mathematics. Okay, I'm told, well, my biology colleague calculated that we're really in this case in South Asia after the monsoons. So if the threshold for infection is greater than the natural carrying capacity of the bacteria, then there's anywhere from 2 to 4 equilibria. There's always a saddle equilibria corresponding to everyone susceptible, so you're not going to see that. There's an attracting equilibrium point corresponding to everyone susceptible and the reservoir at carrying capacity. So for small zeta, that's it. So that means for small zeta, the population becomes disease-free. Right? Because, again, there's only one equilibrium point that's attracting, globally attracting equilibrium point corresponding to everyone susceptible and no infected and the reservoir carrying capacity. So for small zeta, we become disease-free. Okay? Disease dies out quickly. That's good. Then as you increase zeta, there's a saddle node bifurcation at some value. So once you get past that, the parameter corresponding to the saddle node bifurcation, you have two additional equilibrium points. One is a saddle, which we forget about, and the other one is attracting. So what that means is that for zeta large enough, then either the population becomes disease-free or the disease becomes endemic, depending on initial conditions. So, of course, this gives you a strategy to try to prevent the disease, right? You try to make zeta small, and or you try to put yourself in the basin of attraction for this equilibrium point. Okay, I guess I don't have that much time. When we let me just keep going. Here's some real data. This is from a cholera outbreak in Dhaka in Bangladesh in maybe 2003, something like that. So this is weekly data from the second week of August to the end of the year. So you're seeing three types of data here. This data corresponds to the number of infected. The black bars correspond to the density of V. cholera bacteria in the water. And these guys did something, these investigators did something which no one else did before. They also collected phage data. So this is the phage density in the water. Okay. Now, we tried fitting our model to this data using these initial conditions and using parameters we get from the literature. Terrible fit. Terrible fit. Not so bad I'm not even going to show you. But I will show you something in a minute. Now, what these investigators did staring at this data, they said, one way of interpreting this is as the phage density increased, the number of infected decreased. And the density of the cholera bacteria decreased. So they speculated that it's a cause and effect, that the increase in the phage was killing off the cholera bacteria and was responsible for ending the outbreak. And the question is, does that make sense? So can we show that this is possible using a mathematical model? So just give me 2 more minutes if you don't mind. We took the model I just showed you and we added phage control of the bacteria. So this is recent work, and I'm showing you there are no theorems here. It's numerical simulations. So it's the same system. Again, I'm suppressing natural births. For bacteria, where this term, and I'm not telling you what f of b is, but it's something which is as realistic as we can get. This corresponds to the death term of bacteria corresponding to phages. And here we have the phage growth term, which corresponds to the growth of phages and the natural death of phages. So what we did was we took this extended model. We used, again, the best initial conditions we can find. The best parameters we can find. We used these 3 initial conditions, and this is what we got. So the blue curve is the output of our model, which is the number of infectives over time. And you're supposed to compare this blue curve to this black curve. And you see this peaks after like 3 weeks, and this kind of peaks after 3 weeks. So the timing is right. The green curve corresponds to the density of bacteria in the reservoir. That corresponds to these black bars, and it's not bad. And finally, this green curve corresponds to, it's the output of our model. It corresponds to the phage density, and that should correspond to these light bars. And again, it peaks, our phage density peaks at, 8, 9 weeks, and seems to be here too. Yes? Light what? Yes, yes. No, yes, there is. This is preliminary, but there is. There's certainly a slight time delay. I don't know what's going on with that. So, what can I say? So, for our model without phages, the cholera becomes endemic. Okay, we know outbreaks end after several months. So this is wrong. For our model with phages, and again, let's go back here just very quickly. The number of patients, number of infected blue, goes to 0 essentially after 10 weeks with the phages. So for our model with phages, the cholera outbreak dies out. So our mathematical model shows that it's possible that in real life the phages are killing the V. cholera bacteria and ending the outbreak. So this gives some motivation to biologists to study the biology of this and do field studies and see if this is what's really going on. Okay, let me stop here. Thank you. Actually, wait, hang on one second. I just want to show you one picture, which is what I'll use to begin my next talk.